The starting room in the spire has a sign that says there are 1,600 paths. Where did that number come from? Well, it came from me, the spire's chief combinatorialist, the most irrelevant team member of them all. And since unlike most people I have exactly zero skill at the game, I'm making a math video on the spire instead. So how did I get that number? How can we generalize? What will we learn along the way? This is Why 1600. So first I deleted all the blocks that weren't bedrock, and then I put straight line paths made of blue stained glass in every room, showing where you can go from each room. And then finally I cleared all the bedrock away too, and that leaves us with this life-size model showing where all the rooms are and where you can get to from each room. Or we could have used this model in the basement. Anyway, now that we know the layout of every part of the map, we can start counting. So when I was asked this question, the strategy I immediately thought of is to replace the question, how many paths from the bottom room to the top room, with the question, how many paths from the bottom room to every room. Now, to be sure, this is replacing one question with exactly 44 questions, but this actually simplifies the process so much that I can show you the entire thing on camera. So let's start at the bottom room. Now, there's only one way to go from the bottom room to itself. You just go nowhere. So this gets assigned a 1, and I build a 1 on top of the room. Each of the rooms above it is also going to get assigned a 1, because there's only one way to go from the bottom room to each of these rooms, because it's just a straight line path. So I build a 1 on top of each of these rooms. Now, level 3 is where it starts to get more interesting. Oh, what's going on here? Oh, I need to fix that. Okay, that's fixed. So level 3 is where it gets more interesting. The corners still are only accessible in one path. You have to kind of be on a mission. So these still get a 1, so nothing new there. And all 4 corners will get a 1. The sides are a little bit more interesting. You can convince yourself that the only 2 ways to get up to a side room from the bottom room are these 2 arrow-shaped paths. So the rooms on the sides will be marked with a 2, which is a little hard to build, but I think I did a relatively good job of it here. And so all 4 of the rooms on the sides of this layer will be marked with a 2. And then finally the room in the middle, I guess, is the hardest to count, but you can see that there are 4 ways to get into it, 1 from each of the rooms below. And I think this maybe actually gives a slightly faster way to count this. So rather than counting the paths all the way from the bottom to the room we're looking at, we can just add the numbers of the rooms that feed into the room we're looking at, right? Because each of these rooms below it will contribute 1 path. And so we get 1 path from one of these rooms and 1 path from another, and in total these add up to 4 paths. So this room will be marked with a 4. Okay, so that's that layer done. And we can move on to the 4th layer. So again, the corners are once again marked with a 1. This room on the side is above rooms marked 1 and 2, so it gets marked 3, because 1 plus 2 is 3, famously. This other room on the side is also going to get marked a 3 by symmetry. You know, the whole spire is symmetric, and the corners, again, is getting a 1. And then this room in the middle is above rooms marked 1, 2, 2, and 4. And 1 plus 2 plus 2 plus 4 is 9. So I write 9 on top of this room. And there are 4 central rooms, and by symmetry they're all going to get marked 9. And you can continue this process for this whole layer. So that's what the numbers look like. We can now move on to the 5th layer, where they start getting smaller, but the process of adding up the numbers remains the same. So this corner room is now above a 1, a 3, a 3, and a 9, and those add up to 16. So this room gets marked with 16. I'm using signs now because numbers won't fit anymore. These rooms on the sides are all above a 3, a 3, a 9, and a 9, and those add up to 24. So this room gets marked with 24. The corner again gets a 16. And then this room in the middle is above 4 9 rooms. And 9 plus 9 plus 9 plus 9 is 36. Not 362, 36. And from then on, we can just complete this layer. So it's another 16, another 24, and another 16. And above that, the numbers are actually going to get very simple. So all of these 4 rooms on the 6th layer are above a 16, a 24, a 24, and a 36. And those add up to 100. So we're going to put 100 on top of all of these rooms. And the 7th layer is above for 100 rooms, and 4 times 100 is of course 400. So each of those is contributing 100 paths. So this one gets 400. And then finally something weird happens on the 8th layer, where this 400 room feeds into the top room 4 different ways, so it contributes its 400 paths like 4 times. So we multiply by 4 and we get a total of 1600. So there you go, that's the number. If you just clicked for the number 1600, you can click off now, because that's the number for the spire. And this is actually exactly the thing I did when I was asked this question back in July. But what happens when the Spire 2 comes out and it has like 11 layers instead of 8? Or like 111 layers? Any volunteers to repeat the process? We'll definitely need a more efficient method. So I don't know if there are any plans or concepts of plans for the Spire 2, but when I imagine it, I imagine kind of a scaled up version where the layers start at 1 by 1 and go to 2 by 2, 3 by 3, 4 by 4, 5 by 5, 6 by 6, and then they start getting narrower, right? So it goes to a 5 by 5 layer, a 4 by 4 layer, a 3 by 3 layer, a 2 by 2 layer, and a 1 by 1 layer at the top. And I'll be assuming that there's no funny business with the quadruply accessible final room, so that means there are always an odd number of layers because of the middle layer. So let's say there are 2n plus 1. And I want a general formula for the number of paths in a 2n plus 1 level spire, and the method from before just isn't going to work for that. So we'll need a new way to count the paths. So here's some random path in our huge 111 layer spire. And you know, this is a very kind of complicated 3D object. It has free reign to kind of snake through 3D space in almost unlimited ways. But we have a way to simplify it, right? We just look at the entire path head on from the x direction, and now the octahedron looks like a rhombus, and the path looks completely flat. Now, to be sure, this does lose information, like here are 2 different paths that look the same when we look at them from the x direction, but we have a trick. We can recover the lost information by also looking at the path from the z direction. Now, we kind of obtain 2 images from any 3D path, the x view and the z view. And what's more is if we only have the x view and the z view, we can reconstruct the original 3D path, because the x view on a particular layer gives the z position of the player when they were at that layer, and the z view gives the x position of the player when they were at that layer. And so if we have both of these pieces of information, we can find out the exact position of the player when they were on that layer, and so we can find out where they were at all layers, which is the same as knowing what their path was. So this means that the number of 3D paths is in one-to-one correspondence with the number of pairs of 2D paths. So if we find all the 2D paths, let's say there are c of them, then there are c choices of the x path and c choices of the z path, and all of these pairs make a valid 3D path. So that means there must be c squared total 3D paths. So here the rows look the same when you look at the z direction, and the columns look the same when you look at the x direction, but overall all of these 3D paths are unique. But we still need to find how many 2D paths there are, so let's inspect them a little more closely. So here's some rhombus, and here's some random 2D path in the rhombus. And you may notice that this can be encoded as a sequence of right moves and left moves, right? At most places, our player can go up and to the right, or up and to the left. And this can be kind of simplified as a sequence of R's and L's. And any 2D path will have one of these RL sequences, right? And what's more is if we track the horizontal position of our player as they move from the bottom room to the top room, they have to end directly above where they started, which means they have to go right as many times as they go left. Since there are 2n+1 layers, and each R or L is between two layers, there are exactly 2n total R's and L's. And if there are as many R's as there are L's, there must be n R's and n L's. And it's not too hard to check that any sequence of n R's and n L's will make a valid path that will never leave this rhombus, which means that if there are C paths, there are also C sequences of n R's and n L's. But how does this help? We've just transferred the question over to counting sequences of n R's and n L's. So, what are we going to do? Well, it happens that the painters have arrived, and they've chosen n colors of paint, and they want every R to be painted with a different paint color, and every L to be painted with a different paint color. So here's one way to do that, right? Every R gets a unique color, and every L gets a unique color. And the painters ask, how many colorful sequences are there? Well, to answer this question, we have a couple ways to solve this. One way is this kind of three-step process, where first we choose a uncolored R and L sequence, and we know from before that there must be C of those. And then we choose an ordering of the colors for the R's. So there are n colors, and there are n positions, right, where those n colors have to go. And so since they can be ordered in any order, there must be n factorial possible choices at this step. And then we do the same thing for the L colors, right? There are n colors, so there must be n factorial orderings. And all of these choices are independent, right? None interferes with another, so they multiply, just like before. So there must be n factorial times C times n factorial total colorful sequences. But we also have another way to count this that kind of does away with this entire complicated three-step process and sees the colors as painted on permanently to the letters. And now there are 2n different letters, and there are 2n positions, which means that there are 2n factorial total orderings. Now what does this mean? This means that n factorial times C times n factorial is actually equal to 2n factorial. Isn't that interesting? The painters can leave now. Just to recap, we have two different ways of looking at these colorful RL sequences. One is a blank RL sequence that has had colors added onto it, and this multiplies the options by a lot, in fact by n factorial n factorial. And another way to look at it is as 2n free floating letters that have to be ordered in some way. But in the end, the objects, these colorful sequences, are the same, so the two ways of counting them are equal in value. So if we divide both sides, we find that C is equal to 2n factorial divided by n factorial times n factorial. And there's actually a special name for this formula. It's called the central binomial coefficient. You don't need to know that. This is just kind of novelty fact. But remember, we're not actually looking for C. We're looking for C squared, which is just going to be the square of this fraction. And this squared fraction is the actual answer we are looking for, the number of paths in a 2n+1 level spire. Now, to check this is right, we can try it on, the spire we calculated previously, where there are 7 normal levels, or n equals 3, and this formula gives 400, which, if you remember, this does not account for the funny business with the final room, so this is correct. It does not multiply by 4. So that's for a 7-layer spire. But for a 9-layer spire, this formula gives 4,900 paths. For an 11-layer spire, it gives 63,504 paths. And for a 111-layer spire, it gives this many paths, which I will not attempt to pronounce. From what I've said so far, there's a couple of facts about the room count numbers we saw before that you can prove. So one pattern that holds up to the middle layer, the largest layer, is that the sides of these squares are rows of Pascal's triangle. Another pattern that holds on any layer, say this layer, is that if you draw a rectangle with vertical and horizontal sides, say this one, and then you multiply the numbers in opposing corners, you'll find that the products are the same. So in this case, we find that 120 times 225 is equal to 90 times 300. And this will work for any rectangle on any layer of any spire. So proving that result is your challenge for this video. Something else that's interesting is we can use something called Stirling's approximation, which I won't show here, but you can use it to derive that the formula from before is approximately 16 to the n over pi n for large n. Kind of surprise appearance of pi. And to check this, this is the exact number of paths in a 111 layer spire we calculated before, and this is the approximation that this gives. So you can see it gets the exact correct order of magnitude and the first two digits, which is not as much as I was hoping for, but it's not too bad either. So that's it. Thank you for watching to the end, and let me know if you want more math content or if you do not. Bye.